Again, welcome to Physics 4B. Basically, we are in the Tuesday session. Today I have, today basically what we want to do is, because chapter 27 actually was, we introduced chapter 27, and it has two actual things in chapter 27, two main points basically from chapter 27. Both of them deal with the same thing, and they say basically what does the magnetic field does. Okay, the magnetic field affects a charge, moving charge, not a fixed charge, not a stationary charge, by exerting a force on it, which is QV cross B, and it involves that nasty thing, which is a cross product. But that's one thing. Then we took that idea and we looked at the current, basically in a wire, so a wire carrying a current. And we saw also the effect of the magnetic field on that too. And that turned out to be also a force. So it's going to bend the wire one way or the other, depending on which way the force is pointing. And, excuse me. And that force is actually also given by the expression, which is the current I. The key point in here, I has to be steady current, okay? I times the length of the wire crossed with B. So those are the two main points from that chapter. I'm going to defer the problems with chapter 28, because chapter 28 is really an interesting thing, and it's really what we get to the meat of the subject in terms of the things that needs to be done. Okay, so let me share with you my screen. Okay, and once I share with you my screen, basically we're going to go through the stuff that we need to do in here. We have a lot of materials for this to cover from now toward the end of the semester. Basically, we have 6 chapters altogether for exam 2 or midterm 2, if you want to call it that way. We have chapters 27, which is already is going to be combined with 28. And chapters 27 and 28 can be summarized in 2 words. The causes, the effects of magnetic field that I just mentioned, and also the causes of the magnetic field. Those are the 2. Then chapter 29 deals with the non-static situations. Basically, now when you have a situation where the magnetic field changes with time, or the wire goes in and out of the magnetic field. So in here you have an effect which is called the magnetic induction. So we're going to introduce that in chapter 29, and that leads us to Faraday's law. Chapter 20, or is it 30 will introduce another concept called an inductor. So by then we would have discovered the resistor, would have discovered the capacitor, and now a third device called the inductor. So that is chapter 30. Chapter 31 really takes all of these 3 components that I mentioned, basically resistors, capacitors, and inductors, and a new source of power, not a DC battery, not a static battery like the one I have in here, like this one, but rather an alternating current. Combine them there, all 3 of them, or at least all of these devices, in AC circuits. So instead of dealing with DC circuits, where you have a resistor and a capacitor, for example, and you go through a process of charging, which is time independent, but then because the source in that case is actually a fixed source, let's say, for example, you have 90 volt, you have 90 volt, doesn't change with time. So, but in the situation, what we have an AC source, okay? And the AC source, what it does in this case will cause the circuit, the RLC circuit, resistor, capacitor, and inductor, to oscillate, okay? There are 2 kinds of responses to the AC current. There is the so-called transient behavior, which is really an unavoidable thing to have in any circuit, but then you have the steady state current. That is the one that really what you want out of your circuit, is the steady state. So that's the 2 concepts that we're going to explore in chapter 31. Then we abandon everything on chapter 32 and say, you know what, we're going to be in a region of space where there are no currents, where there are no charges. We're going to be in free space. That's what we call it, free. Free meaning that there is nothing in it. It's completely empty by itself. No charges that can cause electric field, or no currents that can cause magnetism, And now we want to solve Maxwell's equations, basically bare, naked completely from those two, okay? It turns out the solution will be the electromagnetic waves, okay, the EM waves. So and that will conclude the entire basically course for this electric field and magnetic field. And you will see toward the end that both of them are actually the same thing. Electric field and magnetic field turn out to be two sides of the same coin. So this is in a nutshell for the entire class for Physics 4B and how it's laid out, okay? So let me introduce chapter 28 because it's critical. It's going to answer the question is, what is magnetism? What causes magnetism, really? So let me share with you. I'm going to share instead of screen, I'm going to share just the, because I may have stuff in there. But, okay, so I'm going to put this on this side. Okay, so chapter 28. So let me summarize first of all what we saw in chapter 27. Chapter 27 basically gave us another force now acting on a charge due to a magnetic field. That charge better be moving. It cannot be stationary because if B is 0, this force is 0. And it's given by this expression. So this is the cross product. If a charge happens to be also in an electric field, it's subject to the electric part of it, an electrostatic field, which is simply QE. So in a sense, this is actually easier than this one because of that cross product. Okay. So in general, a charge can be subject to both forces. A charge, Q, if it happened to be in an electric field, so it's subject to this force, but if it happened to also move inside the magnetic field, it's subject to this one. So this one has a name. It's called the Lorentz force. Okay, so this is basically in a nutshell what this we discovered then. And also, we also saw if I have a region of space where there is a magnetic field, and I happen to have a wire in that region of space, so this is a wire. Okay, I'm going to draw it straight in here, wire. So in this case, this wire has a length L, given length L, and I'm going to point the direction of L in the same direction of the current. Because the length really is not a vector, it's just a measure of how long it is. So it's going to be something in meters. And I'm going to give it a direction nonetheless, and the direction is that of the electric field. So that will be subject to a force that is given by this expression, IL cross with B. So this is a wire carrying a current I inside a region or inside a magnetic field, the B field. Okay, so if you have a wire, then it's going to bend one way or the other depending on how this cross product will result. Obviously, if L and B are parallel, this thing will not bend one way or the other. Because if two vectors are parallel, the cross product between A and another vector that is parallel to it, I'm going to write parallel A, okay, another vector. No matter what happened in here, it's going to be the length of the first times the length of the parallel vector. It doesn't matter how long it is. So their length times the sine of the angle between them. And the sine of any vector with a vector that is parallel to it is 0 degree. So when you multiply by sine of 0, which is 0, the whole thing is 0. So if this two happen to be parallel to one another, then hey, listen, there is no force in them. We're done. Okay. But if it's any other direction, then of course there is a finite value for theta, and that will give you a finite value for the cross product. So this is in a nutshell what we saw in chapter 27. Okay. Chapter 28 deals with the sources of magnetism. And hopefully at some point we should be able to answer what is even a magnet, a regular magnet, okay? So sources of B. So people experimented with this idea too, when they were experimenting with it to see exactly what can cause a magnetic field. So if you have a charge that is moving, it turns out it's going to affect the compass, and it indicates that there is actually a magnetic field for it. So if we measure that magnetic field due to a charge, so this is B due to a simple charge moving in space, it's going to be given by, first of all, mu naught divided by 4 pi times Q times V crossed with R hat divided by R squared. Let me explain what that R hat means and what this numbers means and all of that, okay? So imagine with me for a second that we have a charge in here moving in space. So it has charge Q and this is its velocity. I go somewhere in space, this point in space. And I want to find the magnetic field in that region due to this charge. So this is a point P in space. The vector or the distance between it and where the charge is at that instance is this distance R. The unit vector points from the charge, where it is in space right now, to this one. So that's where R hat is. Mu naught is the permeability of the vacuum or air. It's the same thing, okay? So mu naught is just a constant. Mu naught is equal to 4 pi times 10 to the negative 7, the proper units now. We know the units for B is in Tesla. This has no units. R hat is just a unit vector times the units for the charge, which is going to be a Coulomb, times a meter divided by second. So let's plug in the numbers in here so that we see. So on one side, we have a Tesla. 4 pi has no units, so I don't care about it. The units for mu naught times the units for, so according to this formula, the units for Q is a Coulomb. The units for velocity is a meter per second divided by 1 over meter squared, the distance squared. Cancel one of this meter with that meter, and a Coulomb over a second is actually an Ampere, okay? So that to express everything in terms of SI. So what happened in this case, the units for mu naught will turn out to be Tesla times a meter divided by an amp, because the meter will go up and multiply. So the units for it are in Tesla, meter per ampere. So this is the units for mu naught, and this number is very, very tiny. And like, if you guys remember, a point charge by itself will create an electric field, if you guys remember from previous, which is just a rewrite of Coulomb's law, 1 over 4 pi epsilon naught times the charge divided by R squared times R hat. So again, this is similar to that. This, from the get-go, involves cross product. So it's a little harder than the other. And it's perpendicular to R hat. It's not in the same direction of R hat. So if you're asking me, where is this going to point? I tell you, I'm going to draw the vector V in that position, or at least a parallel to vector V. So this is how vector V would look like, which is the same vector V in that. And I'm going to form the cross product. So this angle is theta. So if I'm going to do the math in here, so it's going to be the magnitude of B is just mu naught over 4 pi times Q times V. This is a unit vector, okay? Times the sine of the angle between them, which is sine of theta, divided by R squared. So this is how much numerically it is. But the direction is perpendicular to both R hat and theta, given by the right-hand rule. So this is where V is pointing upward, like this. You have the thumb has to point to where V is. R points to where the what is this? The index is. Okay, and then the velocity V and the product of them is where the other one completes it. So according to this picture, the magnetic field should be going into the screen. Actually, the magnetic field is inside the screen. This is where the magnetic field is pointing. It's going in, okay? Because if these two, namely the vector V and the vector R hat, are on the plane of the screen, then no matter which way you're going to cut it, the magnetic field can only be in or out of the screen. That's it. Because it cannot be on the screen. Because it has to be perpendicular to both R and the vector V. In this direction, actually, V to R, not R to V, okay? So in this situation, the only way it's going to be, it's either going to the screen or out of the screen. But if we use the right-hand rule, which is really what we have to do, then the right-hand rule in this case is going to indicate that this is going into the screen. So that is basically how we understand this one. And like this one, if I have a charge sitting by itself in here, not necessarily moving, if you have a Q in here, and I want to find the electric field in here, so the electric field will be parallel to R hat. So this is easy, because all you have to do is just find this scalar, which is a number times R hat. So if this number happened to be 150 newtons per coulomb, that's the answer, okay? That is the answer to that, times R hat. So it's going to be this 150 times just R hat. But it's parallel to R hat. It's on the same plane, not only on the same plane, but also parallel to it. So this is a little bit of level of difficulty when it comes to dealing with the magnetic field, is that cross product which appears every which way. That's one thing. The other thing also is this mu naught and epsilon naught. Mu naught by itself, and I'm kind of a little bit disappointed, honestly, with the exam, that some people did not pay attention to the fact that they gave the value of 1 over epsilon naught already as being 4 pi times 9 times 10 to the negative 9, okay? I'm sorry, 10 to the positive 9, okay? And the units for it, again, you can use whatever units in here. This is a Newton per coulomb, and this is a coulomb. So it's going to be downstairs, coulomb squared, and you're going to have a meter squared in here somewhere, okay? So it's going to be Newton meter squared over coulomb squared, okay? But ignore the units for a moment. Just look at the powers. 1 over epsilon naught is the one that is going to impact the electric field. Not epsilon naught. Epsilon naught is a small number, because if you invert this one, it's going to be 10 to the negative 12. But it's actually epsilon naught downstairs. So when you divide by a very tiny number, the number is huge. It's 10 to the power 9. Okay? This one, actually, you multiply by mu naught, and mu naught is still small. So from the get-go, it looks like there's two scaling, two values. One of them is the permittivity, epsilon naught. It's the permittivity. Permittivity, and the other one is the permeability. Both of them impact the expressions differently. Everywhere we dealt with epsilon naught, we had it in the denominator. The only exception when we were dealing with the energy density for the electric field, we found it to go upstairs. Okay, that was the exception, by the way. Everywhere else we had epsilon naught, it was in the denominator. Now it looks like mu naught has switched places. It came in the numerator, okay? So this is an important fact, because at some point also, I'm going to be calculating the energy density due to the magnetic field. And I would want to track what happened to mu naught. So I would want to know, is mu naught going to stay what it is, or is going to flip places? Because if it's flip places, instead of coming in the numerator, it should come downstairs, okay? That is one thing. Obviously, instead of having the electric field, I should have the magnetic field, and this is probably a factor of half stays the same. So this is not necessarily a proof, okay? But it's probably what's gonna happen, okay? So by symmetry, probably that this is it's a probability, not a real deal, okay? I did not prove anything at this point. All I'm saying is that because we saw what happened with epsilon naught, that everywhere we dealt with in every single problem that leading up to today, up to at least anything, it was in the denominator. The only exception was when we dealt with the energy density. So this was the energy density, where for some reason it found itself in the wrong place. So what I'm saying in here, keep a watch on mu naught, okay? Mu naught from the get-go, it came in the numerator. It did not come in the denominator. It came here in the numerator. So is this going to be the same thing everywhere where we're dealing with this expression that's going to be in the numerator? And then when we're dealing with the energy density for the magnetic field, which I'm speculating, so this is a speculation, not necessarily a proof of whatsoever. It's a speculation that maybe is going to migrate downstairs, just like what happened to epsilon in here, except in the opposite direction. And maybe instead of having the electric field squared, they will have the magnetic field squared. And maybe this 2 is inherent, or 1/2 is inherent to the expression that they will have it again. Obviously, the reason why I'm saying that is because actually this is a fact, and we're going to prove it down the road. This is not a speculation, it's a fact, okay? And I want you guys to hold me to this fact down the road to show that the energy density for the magnetic field is that expression, okay? So let's continue. That's one thing. That's for the how charge creates a magnetic field. Well, people did not really experiment with the charge as much, honestly, with the wire they did, okay? So if you have a wire in here and you zoom in, so it has a current running through it every which way, okay? So if you take this portion of the wire, it's a tiny portion. So there is a current I running through it. You take this portion in here and you blow it with a microscope, for example, and you see the effects of that portion of the wire. So this is the same portion I was talking about in here, okay? So it has a length dl. I'm going to take that dl to be in the same direction of the electric field, the current, I'm sorry. If the current was going this way, so that is the direction of dl. So the dl is pointing this way, okay? And let's say, for example, for the sake of argument, I want to find the magnetic field produced in this point by this one. So this is the distance r. The unit vector I'm going to choose in here is r hat, from where the wire is to where the point I want to find the magnetic field is. So don't ask me now to tell me, are you going to change the beginning of the or the beginning of the wire or the end of the wire or somewhere in the middle of the wire? The whole thing is d. It's an infinitesimal quantity. So it doesn't matter where you put it, okay? The starting point. The whole thing is small, tiny thing. It's going to go to 0 actually in the limit when we do the integration, when we sum, okay? So it doesn't matter. So I took it in the middle, but you can take it anywhere. Besides, this whole wire is actually very thin, so it doesn't matter. We just took it to their microscope to see how big it is, okay? So then this is the law that they have found, that the magnetic field due to that element only, so this is not the total magnetic field due to the entire wire. So if I'm interested in the entire wire, I really have to sum. I have to do integration. But due to that wire only, it's given by mu naught over 4 pi times the current I running through it times dl crossed with r hat divided by r squared. Okay, this is known as the Biot and Savart law. So there is no proof for this one. This is an experiment. This is based on observation. It's like a law. I mean, it says a law. Okay, this is our starting point. This is something that basically people have experimented and spent a lot of time trying to find the magnetic field. Obviously, this quantity is an infinitesimal quantity, and technically, I really have to integrate and sum through different regions of the wire to find the finite value of the magnetic field. Otherwise, it doesn't make sense, I mean, to work with this one. Okay? So this is an experimental law. Okay? So let's see where this would lead us to find, okay? And I will tell you the main points of this chapter at some point. But I'm just trying to bring the background in here information so that you have enough of it. This law is complicated. I mean, when we were dealing with the chart before and we did that, it was a little bit easier, honestly, for the electric field than this one because of this complication of this cross product that we have to do. Look at this magnetic field. It's not in the direction of dl at all. It's not in the direction of r hat. It's actually in the space perpendicular to both of them. As a matter of fact, I can represent my dl in here. And it involves the sign of this angle. Again, if I use the right-hand rule, actually this one is going to point outside. This one, the magnetic field looks like this. It's coming out of the screen. Oh man, Rosie. So it's coming out of the screen, okay? It's like a pointy thing, it's coming out. So it's not in any of these two. So if both of them happen to be on the screen, again, this cross product will involve that one. So it involves the sign of the angle between them. So let's calculate this one for an infinite long wire, okay? Straight wire, because it's easier to do the summation over a straight wire. Yeah, let's have it in. No, let me draw it in blue here, and let me draw it actually in black. I'm sorry. me draw it in a very super thick wire, okay? So this is a wire that has a current in it, running through it. And I want to come, so there is a current in here that is running I. And I want to go somewhere at a distance Y from the wire. And I want to find the magnetic field at that point, okay? Because the wire is infinite, it doesn't matter where you are. Okay? So the wire has an infinite length. So it doesn't matter where you are. So I'm going to take this one as the origin of the x-axis. So this is my x-axis. And I'm going to go distance x from it. And a distance x plus dx. Obviously, dx needs to be tiny. I'm just drawing it in here so big so that we can see what's going on in here. And I'm going to take, this is actually the r we're talking about. Since this distance is x and this distance is y, you can clearly see from the Pythagorean theorem that this is x squared plus y squared under the square root. So that is the distance. Obviously, this is where r hat is. So it's this vector. This is my r hat. And you can clearly see, according to my arguments in here, that the length dl is actually dx in here. This is the dl now. So this is dx. And it's in the x-axis. That means this is in the I hat direction. Okay. So this is basically, in a nutshell, the geometry of the shape that we have in that we are dealing with at this point. Okay. Can you draw this triangle in here? Again, I like this thing in here. No, it has to be in it. I don't like this. Can I have another shape in here I can draw? No, hate that. Okay. So I'm gonna draw this triangle in here again, and hopefully to see what's going on in it. Come on. Okay, so this is more or less the triangle that I have in here I drawn. So this is the x, this is y, and that is that r basically, which is just the square root of x squared plus y squared. Okay, I'm gonna call this angle theta. This is the angle theta in here. And you can clearly see from the geometry that tangent of theta is equal to x over y, because the opposite is x and the adjacent is y in this right angle triangle. Okay. And so we're almost there. The only thing I have to do is find the r hat in here, this vector r hat. Okay. It's either you draw it in here or you draw it in here. It's the same r hat, basically. This is the same r hat. So r hat in here, it's actually equal to the vector r itself divided by r. And the vector r itself is actually x components in the negative direction, because x is actually positive this way. So I really have to write it as minus x I hat plus y j hat divided by r, which is that square root of things that we need to get rid of the things. Okay. So that is basically how the vector r hat is. This is not r, this is the vector r hat, I'm sorry. Which is the entire vector divided by itself. So that is actually the unit vector. Because you can write always r as r itself in length times r hat. So that is any vector parallel to r hat can be written in this format. Any vector a that is parallel to r hat can be just the length of a times r hat. So that is basically what I'm writing in here. So r hat would be just the ratio of that r over r. Okay. It's clear from the geometry that x is the opposite to theta. So x over r is simply equal to the sine of theta. And it's clear also that y is the adjacent to theta. Y over r is equal to cosine of theta. So if I sub these values in this expression, that should give me what r hat is. So r hat then is equal to negative x, which is r sine theta, I hat, plus y, and y is r times cosine of theta in the j hat direction divided by r. Obviously, the r and the r and the r cancel because we really don't need that. I mean, that's an added complication. So it's minus sine theta of I hat plus cosine theta of j hat. And you can quickly check that r hat in length is equal to the square root of negative sine squared, that's sine squared, of theta, and positive cosine squared, that's positive cosine squared. And sine squared plus cosine squared is 1. So the length is indeed 1. So this is really a unit vector. Okay, so it's truly a unit vector that we're dealing with at this point. Okay, as it should, because regardless of what theta is, this is always 1. Its length is always 1 because its x component is negative sine theta. So when I square it, it's going to be sine squared theta, and its y component is cosine theta. So when I square it, it's cosine squared. And there is that identity in trig that says sin squared plus cos squared is always 1, no matter what that angle is. So in this case, we have r hat. The reason why I need that is because I need to combine everything in this cross product. dl, which is just this element in here. And now I'm going to write the magnetic field due to just that part, dl. So that is dB. And dB is given by the expression that I mentioned before, 4 pi over times the I times dl crossed with r hat divided by r squared. We're almost there, okay? Because we have dl, which is the x I hat, and we have r hat, which has this combination of I hat and j hat, and we're going to find the cross product of these two. So let's do the cross product now to find what dB is. So dB is equal to mu naught I over 4 pi r squared. Those are constant. They don't impact the cross product. Times, I am going to write the determinant method, ijk. Let's look at dl. dl is entirely in the x direction. It's dx I hat. That is the direction of the wire, the infinite wire. So it's dx, 0, 0. And the components of this vector r hat are minus sine theta, positive cosine theta, and 0. If I form the cross product, first of all, in the I hat direction, I will have 0 squared minus 0 times cosine theta, and that is equal to 0. 0 minus 0 is 0. In the j hat direction, I have a negative j in here, the negative j hat, times dx minus 0, that is 0. 0 times minus sine theta, that is 0. So I will also have 0. The only product that is not going to give me 0 is in the k hat direction. In the k hat direction, I will have dx times cosine theta minus sine theta times 0, which is 0. So at the end, the only component that is going to survive is in the k hat direction, and that component is coming from these two terms only. So it's going to be mu naught I times cosine theta times dx divided by 4 pi r squared k hat. That is the only thing that is going to be left for this quantity. Obviously, I need to sum dx from negative infinity to positive infinity. I already have the expression for r is equal to square root of x squared plus y squared. When I square it, it's going to be simply just x squared plus y squared. But I have that annoying x cosine theta. I have two ways of handling this situation. Either use this identity and write x as being y tangent theta, and take that advantage and convert to theta, which I'm going to do actually, by the way, or basically find the cosine theta as a function of tangent, which is square root of 1 plus tangent square theta under in the denominator, and sub the values of the tangent theta, which is going to be x squared over y squared, and integrate straight out in x. And that is actually not a good way of doing it. You're going to get the same answer, but that's not a recommended way of doing it. So what I'm going to do is I'm going to take advantage of this relationship between x and theta and actually change the variation, the integration from dx to d theta. So we know that x is equal to y tan theta, and it's coming straight out of this expression. Because just that's it. X over theta, y is equal to tangent of theta. So that means x is tangent of theta times y, that's all. So that's exactly what this, y is constant, by the way. We want to find the magnetic field in that point, okay? So let's skip the direction now, because we know k hat now. We know x direction is this way, the y direction is upward, and the k hat is coming from the screen. So we know in this region of space that the magnetic field is actually going to be, did I write it here? So that arrow that I draw was wrong because I didn't actually do the work. Here is what I know about the magnetic field. It's coming out of the screen, okay? But that's its value there. That is its numerical value that I wrote in there. So that's correct. But so the numerical value is this stuff. The direction is actually k hat. It's not the x-axis. It's not the y-axis. It's not the entire plane at all. It's not anywhere on the screen whatsoever. It's coming out of the screen, okay? But that is the value of the magnetic field now. So I'm going to take this variation and try to find what dx is in terms of d theta. So dx will be simply equal. This is constant, so we don't care about it. The derivative of the tangent is a secant squared of theta times d theta. Does this make sense to you guys? Do you remember this transformation? The derivative of this tangent is secant squared?
I can recall this.
Okay, so this stuff is calc stuff. So I'm hoping that you guys, if you are not too sure about it, please let me know. And this is something that you could have done in calculus. So we have the dx, and we need the dx. So it's y times secant squared. All I have to do now is play around with this r squared, and we should be there, okay? So dB now, I'm going to take it only in magnitude, not in direction, is simply mu naught I over 4 pi times, I need to worry about the integrations. Hey, x was supposed to change from negative infinity to positive infinity. Well, sorry, not y. Theta is supposed to change then. Theta is tangent of, arctangent of x over y. When x goes to negative infinity, the arctangent of negative infinity is actually negative pi over 2. And when the x goes to positive infinity, the arctangent of positive infinity is actually pi over 2. In other words, the tangent of negative pi over 2 is negative infinity, and the tangent, at least, goes to negative infinity. It goes to the negative, and then the tangent of pi over 2 goes to positive infinity because the tangent has an asymptotic behavior around these 2 points for the angle. So the integration changes from for x from negative infinity to positive infinity. When we do it for theta, it's actually from negative pi over 2 to positive pi over 2. That's the only thing that is going to happen. So let's write. We have cosine theta. Let's not forget about cosine theta. Times dx. Dx is all of these things, which is y secant squared d theta. I know you're tempted to say, okay, how about if I cancel one of the secants with the cosine? Don't, because actually there is an easier cancellation that is coming through. 4 pi r squared. 4 pi times r squared. R squared is x squared, and x squared is actually y squared tangent theta squared plus y squared. From the here, you can clearly see that the y squared and the y squared and the y cancel. And we're going to take y actually as a common factor. Where do we have another 4 pi in here? Sorry about that. It's already written in here, 4 pi. So it's just r squared that I'm supposed to write in here. I don't have 4 pi squared. So dB now is mu naught I divided by 4 pi y. Because I took the y out, and it would be left with a cosine theta secant squared theta d theta over 1 plus tangent squared of theta. Well, 1 plus tangent squared theta is actually secant squared too. That's why I was hesitant not to cancel any of the secants with a cosine, because that too is a secant squared. So that's going to take care of that secant squared, and we are just left with cosine theta d theta to be integrated from negative pi over 2 to positive pi over 2. So this magnetic field then, the entire magnetic field is mu naught I over 4 pi y, the integral from negative pi over 2 to positive pi over 2 of cos theta d theta. That's why it's a lot easier to keep it in terms of theta, because anybody you ask them what is the integral of cosine theta, they should be able to tell you. So what is the antiderivative to cosine theta? Does anybody remember?
Is the antiderivative negative sine theta? Or
is it negative?
I...
Which one? Isn't it sine theta only?
I usually don't remember my signs here. I have a book.
Okay,
The
that's fine.
test book.
You're not the exception, by the way. Physicists always carry their table of integrals with them. Okay, you're not supposed to memorize these things.
Okay, cool. Yeah, the signs always confuse me whether it's derivative or antiderivative, but yeah.
Yeah, it's a sign table. Okay. Obviously, I have to evaluate it in the upper limit. It's positive 1. Minus in the lower limit is actually negative 1. So it's 1 minus minus 1. So this whole thing is just 2. So all of that work is just to get just this value of 2, which will cancel that 4 pi, and we'll be left with a magnetic field due to a wire being basically equal to mu naught I over 2 pi y. This is a very important result that you need to remember. I mean, you don't want to go through this whole hassle again, okay? This is a very important result. So this is a magnetic field due to wire, an infinite wire magnetic field. So you're asking me, how am I going to get an infinite wire? Well, as long as its length is very large compared to the distance we're trying to find the magnetic field, you can assume it's an infinite wire, and you can use this formula, and you're going to be fine with it, okay? There is another perspective that I should do in here. I'm going to come in here and look at this wire from this perspective, from this angle. So this is how the wire would look like to me, okay, when I'm looking at through that perspective. So this is how the wire would look like. It looks like there is a current coming out. That's it. So if I come in there, yes, it's an infinite, but I'm sitting on the other side of an infinite wire and looking at it. So if I'm interested trying to find a magnetic field in here, obviously the wire is coming out of the screen in here. So if I follow the same rules, actually the magnetic field will be pointing this way. It's on the screen now, since the wire is coming out of the screen at a distance y from it. And if I follow this distance y, it's going to be on a circle, because as you can clearly see, if I don't change y, the magnitude of the magnetic field does not change. It's constant, depends only on y. Since y is fixed, I mean, the current is supposed to be fixed, mu naught is fixed, 2 pi is fixed. So the only thing that is left to fix in here is y. As long as you are in the same y, meaning you are in the same circle, the magnetic field does not change magnitude, but it changes direction. It's always basically tangent to this area. This is opposite to what happened to the magnetic field when the electric field. If instead of a current, we really had a charge distribution lambda, then in that case, if you guys remember, the electric field behaved differently. The electric field was like a hedgehog in here, pointing every which way, opposite to, perpendicular to this surface. So it was really diverging. This one does not diverge, but circulates around the magnetic field. So you can, around the wire. So this one was the electric field, and the other one is now the magnetic field. So the magnetic field is going in a circle. And it's going to be actually a positive circle. We take advantage of that situation now to find the direction of the magnetic field. And it has to be the right-hand rule again, the right hand, not the left hand. So this is the new version of the right-hand rule now. If you take your thumb as being the direction of the current, the way the palm curves around that is what the direction of the magnetic field is. So the magnetic field curves around the palm, around the thumb, as the magnetic field curves around the wire. So you really have to remember that when you're doing your calculations and doing stuff like this one. Now, if the current is going inward, okay, obviously the curling has to happen in the opposite. I cannot really do that. But the point being in here is I can just reverse my hand, and then I'm going to find it curling in the opposite direction. It's clearly curling counterclockwise, okay? Counterclockwise. So that is how the right-hand rule now. So the thumb is the direction of I. The palm, did I spell it correctly? I think that's right. Okay, curves counterclockwise as B. It's a very important result, okay? Very important when you're doing the calculations and things like that one. And the magnetic field is actually curling. It's actually circulating. B is going in a circle. And like the electric field, which was coming out, okay? It's diverging. The magnetic field was emanating from that point. This one does not. It goes around and closes upon itself, okay? The other one will go toward infinity. Hope that you guys see this difference between the two things, okay? Obviously, for the electric field, I have to have some sort of a charge distribution, because even though I have a current in here, the total charge is 0, by the way, because the current, if you guys remember from chapter 25 or chapter 24, I don't remember the chapter 25, basically what's going on in here is that the charge, negative charge is hopping, but the positive charge is sitting still. So at any given point, that part of the wire is still neutral. So if they want to really see the electric field, they really have to have a net charge in here of some sort, okay? I cannot do that with the wire like the way that I'm talking about in here. So I have to have a wire where there is actually sprinkled charge, and then we're going to see the electric field also, okay? Provided that there is actually still current going through the wire, because this depends on I. If I is 0, B is 0. That is the whole point of this whole thing, that the electric field creates the current creates a magnetic field. That says in a nutshell how this thing is working. Okay, let's derive another very important result. And that was part of actually an exam that I gave last semester. And that was the current, the magnetic field created by a loop of a current. So imagine with me that I have a loop of current. I'm going to tilt it a little bit. This is how it looks like. I mean, technically, this is how the wire would look like. So if I look at it on one side, it looks like this. It looks like it's straight wire to me, okay? So this is how this looks like. I'm going to come a distance from it. Oh man, I should have really Control Z. Let me change the thickness so that we're really dealing with what looks like it's a big wire. So we're going to look in here. This is how it looks like tilted at an angle, okay? But since we're dealing with a screen in here, this is how it actually is. If I look at it sideways. Okay, so it's the same wire. Where is my wire? Okay, I have a bunch of them in here. I have a bunch of wires, actually. You can clearly see them in the picture in here. There's a lot of them going around in here, okay? And that is basically the effect. If I have my battery holder in here, I can connect the battery in here, and I'm going to run a current to them. Take any of these wires, and it's going to look like exactly like the shape I have drawn. I have a bunch of them. So whatever I have in here, whatever magnetic field one of them will create, a bunch of them will create as many times that one. So that's basically the whole thing in here. And I'm going to find the magnetic field created on an axis passing by the axis of symmetry. So basically what I'm trying to say in here is, this is the axis of interest to me. So let me change the size again. Is there a way for me to change the shape of the pen? No. I mean, I would rather have a different kind of pen. It doesn't matter. Okay, so this is the axis, what I'm interested in trying to find. These are not two different wires, by the way. It's still the same wire, okay? It's the same loop, I'm sorry, okay? And I'm gonna go a distance x from it, except one of them is tilted, just to give me an impression that it's a loop, actually, but the other one is the actual shape, okay? I'm looking at it this way. So in other words, to go back into my illustration, this is a view of it in one way, but this is the view that you actually should be calculating, this view. It looks like just straight up and down, okay? For you, it looks like just straight up and down. It doesn't look like has that structure, the 3D structure. Okay, so in the calculation, we're going to come back to this shape, but let me illustrate the point in here. So I'm going to come in here to a point distance x from it. Where is my pen? So a distance x from it in here. This is the same distance x, by the way. Okay. I'm trying to find the magnetic field in, that is due to this wire here. So what I'm going to do in here, I'm going to right to the top edge in here. I'm going to take an element in here. So this is the element I'm interested in here. So I cannot see it because it's coming out of the screen. The current is actually flowing this way. Okay. So the current in here is raining down. It's coming out of the screen in here, and it's going into the screener from here. So in here, it's going to go in, and then it's going to go from the other side that I can't see right now, and then it's going to complete on a loop. So there is a current I flowing through everything in here. So I'm going to take an element dl in here, and the element dl in here is coming out of the screen. So it's in the k hat direction already. So this dl, if you wish, is dl k hat, okay? So this is my x-axis. So this is the origin, O. So this is the origin, O. This distance is all of it is x. And this is my a hat direction. So that is basically in a nutshell what I have in here. So this is in representation. This is where r hat is again. And this distance is clearly, I'm going to take a radius r. So this distance is radius r, okay? I know the book takes the letter B, A or something, but it's standard to use the letter r for the loop. So this is a loop in here of radius r, carrying current I, okay? So that is basically in a nutshell what we have in here. At a distance x on the axis of symmetry, we want to find what the magnetic field is, okay? Because the dl is already in the k hat direction, and I expect the value of the magnetic field to be somewhere on the screen, because it has to be perpendicular to dl. And also, it has to be perpendicular to r hat. So this is the direction that I'm interested in. So this is my dB actually, okay? And my dB, this distance, by the way, is equal to square root of r squared plus x squared, okay? So if I go around in here, and around the loop, like I'm doing dl now, changing it, the only thing that is going to change for dl in magnitude is from 0 to 2 pi times the radius r. I would have had the entire circumference. So that is if I do an integration in here. In all of this, the distance r does not change. That's one thing. That's important. It doesn't depend on x. I mean, it depends on x, but x is fixed. We're not moving away from that point. So we're not worried about the integration. The only part that we have to worry about is that just that 2 pi r. So, but as I go along, you can clearly see that this magnetic field now, for every single point, there is an opposing point that if I'm going to circulate, actually I'm going to create a cone in here, okay? And that cone will have no projection in this direction, because for this point, there is a corresponding point on the bottom in here that will have a perpendicular version, and they will cancel. So they will mutually cancel in the direction y, and they will also mutually cancel in the direction z, because this point in here will have a component that is perpendicular, and this point in here, the other side, will have a component that is perpendicular, and they will also cancel. So in other words, it's going to appear like it's a cone like this one. And this direction will cancel, this direction will cancel, every single direction will cancel. The only direction that is going to survive is this direction, because they will add up. So I need to take this angle into account, okay? Provided this is perpendicular, by the way, because it has to, dB has to be perpendicular to r hat. So this angle, which I'm going to call theta, is the same as this angle theta. The reason why I'm saying it's the same angle theta, because both of them, when you add them to this angle, they will add up to 90 degrees. So this is theta, and that is theta, okay? And the projection along the x-axis is going to involve dB times cosine of theta. And cosine of theta from this geometry, this is the opposite. This is the hypotenuse. So just the adjacent, which is r, divided by just this little r, and that's it. So we have everything now to do the calculation. First of all, dB as a vector is equal to mu naught I divided by 4 pi times dl crossed with r. I could have operated similar to the previous session, but I'm just going to give you a different way of doing this in here, okay? dl and r hat are perpendicular. dl is coming out of the screen, and r hat is on the screen. So this product in here will involve sine of 90 degrees. That's why I'm not too worried about this thing in here. That's why I'm doing it this way, so that to make things easy. So dB in magnitude only, and it's going to be in the x direction because all of the other directions will cancel. It's going to be mu naught I divided by 4 pi times at some point cosine of theta. because I need to project it along the x direction, a cosine of theta. Okay? So the denominator is r squared, and r squared from this expression is simply r squared plus x squared. So we have that, r squared plus x squared. And the numerator, we have dl, which is dl, times the unit vector length, which is 1. So this length is 1. So let me write it 1 explicitly so that we don't forget what that is, times sine of the angle between them, and the angle between them is actually 90 degrees, which is also 1. So at the end of the day, all of this calculation will involve, let me write cosine of theta. Clearly from the geometry in here, cosine of theta is simply r over that little r, okay, or square root of r squared plus x squared. So it doesn't change. As long as x is fixed, theta also is fixed. Everything is fixed. The only thing that is going to change is dl going from 0 to 2 pi r. That's it. So this whole integration becomes a little bit kind of easy when we sum through everything through dl. So bx then, which is the entire b, by the way, because there is no other b in here, in the y and z direction is equal to 0, actually, is equal to mu naught I over 4 pi times cosine of theta, and cosine of theta, let me write this expression first of all, 1 over r squared plus x squared times r over r squared plus x squared to the power 1/2. And this is to the power 1, by the way. That's what that means, similar. Times the integral of dl from 0 to 2 pi r. Okay? Obviously, this is just 2 pi r. Okay? Times r, that's 2 pi r squared. And we are in business. So b, which is entirely in the x direction, is going to be mu naught I over 4 pi times 2 pi r squared divided by, so there is an r and there is an r in here. That's why I have an r squared, times r squared plus x squared to the power 3/2. Okay? So there is very little integration, but there is a lot of work. That's what the difficulty with this magnetic field stuff is. Usually that cross product, that the annoying thing is that cross product. Okay, so let's cancel some stuff in here because we have 2 pi and we have the 4 pi in here. So this is actually equal to, so along the x direction. Okay, and it's going to be mu naught I over 2 times r squared, times r squared plus x squared divided by 3/2. Typically, if you guys remember the dipole, this is actually a dipole too, because pi times r squared is actually the area of this loop, pi r squared. And in similar fashion, how we define the dipole moment for the electric field, which was P equal to the charge Q times the distance between the negative charge and the positive charge, we can define actually the magnetic moment in here, mu. This is magnetic moment. It has nothing to do with the magnetic permeability in this case, magnetic moment. If I define that to be simply equal to the current times the area, okay, then that should give me the magnetic moment, and the magnetic field then expressed in terms of that would be simply mu naught times mu divided by 2 times pi, because I have to reintegrate pi again in the expression, times r squared plus x squared to the power 3/2. And that is a magnetic field along the axis of the loop. So if I go back and ask me how much magnetic moment, this one in here, I have to find, first of all, how many of them. Once I find how many of them, I find the area in here and multiply by the current running through it, and I should be able to find the magnetic moment. And then we go back into the calculation. If I put this one inside a magnet, while it has already its own current running through it, it's going to be subject to a torque. And that is what the principle of the motor is. Unfortunately, as I said before, I did not really get any word into the materials for this lab. So basically, we're out of luck when it comes to the building of the motor. So I'm sorry about that. And I know the college ordered it, but I inquired about the status and nobody replied to me. So I have no idea, honestly. So we cannot do that project. But that's something that you could have done and built. And you can still do it on your own. Actually, the materials don't cost that much, about $10, $15 at most. And you can build your motor and actually come up with an estimate for its magnetic moment and the torque and all of the calculation that you're supposed to be doing with an actual motor. Anyway, We can take the dipole approximation. If you guys remember the dipole approximation, we go for distances that's super large compared to r. If we do that, the magnetic field will drop like distance, because this one will be negligible, so it's going to be 0. So you'll be left with an x squared to the power 3/2, and that is x cubed. So we'll have an x cubed. Similar to the electrical dipole, this drops like 1 over distance cubed too. As a matter of fact, one of the very interesting results, we really don't care usually about the magnetic field, honestly, anywhere on this axis other than the center of this one. So for x equal to 0, actually, that was of a big interest to us. For x equal to 0, we sub the value in there for x equals to 0. And then we're going to find b right in the center, okay, to be mu naught times mu divided by 2 pi times r squared to the power 3/2. Again, it's r cubed. So divided by r cubed. But the way I defined this mu, which is simply equal to I times pi times r squared, if I sub that value again, the pi cancels the pi, and it would be, and the r squared cancels the r squared. I forgot the I. No, the I will be restored again in here. So it's going to be 2 times r. So this is actually a result that is needed for a lab at some point in here. So this is the magnetic field inside the center of one, I'm going to write it in capital, loop. So if you have many of them, you have to multiply it by their number, and that is typical. So when you go to, for example, a person that fixes alternators and works on those things for cars, they wrap so many turns. They don't just do one turn. So the problem in here, we're dealing with one turn, but typically in this case situation, you have so many turns, and this number has to have that number n in it. So this is actually a very useful result to remember too. So if you're going to be building in your garage, for example, a motor, or trying to fix an alternator or something like that, this formula comes in very handy. The radius in here, the bigger it is, the weaker the magnetic field in here inside the center, the higher the current, the better it is. And you can actually change the material inside with a material that has magnetic properties, so that its permeability is not mu naught, but rather mu r times mu naught, where mu r is the relative permeability. Then you can enhance actually this one. And this is actually used also on those metal detectors used on the beach. People go and try to collect gold and valuable stuff that is under the beach. So they take actually the current, and it has actually material in it. So when they go and scan, they scan, and based on the permeability of the material that is sitting under the sand, actually the magnetic field will interact with it and change, and the reading will change and actually starts to beep to you and tells you that, hey, there is metal in here. It doesn't know which metal it is. It could be gold. It could be just a piece of junk. Okay, no matter what that is. Well, as long as you can dig, then you can find out if it's something worth keeping or throwing in the trash. So that's just one thing. The other thing also that is used it's used actually in the stop for red lights, for example, in some intersections that are not timed, but rather because the intersection, there is a main intersection and the secondary intersection. On the secondary intersection, you would want the light to be red all the time, except if there is a car coming. So when the car comes in there, again, it has metal in it, and it's going to disrupt because of the permeability properties of the metal, it's going to affect the region in there. It has to do actually with the magnetic induction too, which is the next chapter. But that is actually how cars trigger the red lights to turn and start to go, start the rotation, so that you get green light and you can move on from a secondary road to a primary road. So again, all of this is interesting stuff. It has a lot of applications in it, including this one in here. And they usually use loops for that one, for the under the asphalt. Okay, there is actually structure in that keeps tab that is connected to the red lights, to the intersection lights. Okay, so we covered most of the things that we need to cover. There is a very, very important result that we need to cover. Extremely important. Let me tell you what that is. It's Ampere's law, actually. Let me go through Ampere's law, and it's, if you remember the exam, Gauss's law, this is similar to it. So I'm going to go back into that wire, an infinite long wire, and I'm going to look at it from the other side again. So I have a wire in here, So this is how it looks like coming out of the screen. So it has a current I running through it already. And I was describing in there, this is how the magnetic field on a circle of radius, I'm going to call it R, okay? So this distance is R. So the magnetic field is circulating in here on this. It is always tangent to that circle, okay? So the magnitude of the magnetic field, we just calculated it to be mu naught I divided by 2 pi R, where R is the radius of this area, of this circle, okay? So this is not an area, this is a circle. So I'm going to define the circulation in here of vector B. So this is true no matter what the vector is. But in particular, it's a magnetic field. So it's going to be circulation for the magnetic field. So the circulation of the magnetic field is going around a closed path. This path happens to be a special path, happens to be a circle. In general, it doesn't have to be. It could be any closed path of B times dl, where dl is along the path, actually, is equal to the circulation, okay? So this is by definition of circulation. Obviously, this is a scalar. This is a scalar. This is a number like 12. The reason why is because it involves the scalar product of two vectors. So this is a scalar. But you can clearly see that anywhere on this, so this is dl and this is b. Anywhere in here, dl and b, they're actually parallel to one another. So for the case of the circle, for this special case, the dot product for this case, B times dl is simply B times dl times cosine of 0 between them, and cosine of 0 is 1. That is the dot product, okay? So this is the special case in here that we're dealing with. So the circulation along a circle, and that encloses that current, this circle of radius r, okay, of BDL is simply BDL, okay? So because the properties of the dot product in here, the dot product, two vectors are perpendicular, we just saw that they are perpendicular, that the magnetic field is going to be always tangent to this circle. Okay, it's going to be given by the right-hand rule, expressed basically with the palm circulating around the current. Okay, so on the circle, as long as R does not change, the magnetic field is actually fixed. So it's going to be just mu naught I over 2 pi R. Okay, I'm sorry, 2 pi R. R is fixed because we're going on a circle whose radius is R. R is constant on a circle of radius R times dl, of course. So it's going to come out of the integral. So this circulation will involve mu naught I divided by 2 pi R integrated throughout a circle of dl. And what is the integral of dl of a circle? It's going to be circumference. And circumference is just 2 pi R. So that 2 pi R and that 2 pi R will cancel. And at the end, so this integral and this one cancel. And at the end, it's mu naught I. That's all. So the circulation of the magnetic field around a current carrying wire with a current value I is just mu naught I. That's it. So this is similar to what we did in Gauss's law. We said that the flux of the electric field was a charge Q divided by epsilon naught. So epsilon naught lived downstairs in there and Q was upstairs. This one says mu naught times the current. The circulation of the magnetic field over a circle, or over a circle of radius R, is mu naught times I. We're going to change now the shape to any arbitrary shape. It doesn't have to be a circle. So this is what I'm going to do. I'm going to take the wire now. This is still the wire with the current I, but I'm going to go through a shape that is not necessarily a circle. So any arbitrary path, so here an arbitrary closed, has to be closed though, path. Okay? So what I'm saying in here is the magnetic field is always going to be in this angular direction. So in here, it's going to be in this direction with respect to this one, whereas dl now has two components, one that is radial and one along the angular direction. So B is going to be equal to mu naught I over 2 pi r, where r is less in this situation than in here. R changes now. So we cannot say it's the same because it was the same earlier when we were doing the circle, but this is an arbitrary closed path. So r can be small or big depending on how far we are, times the angular direction, which I'm going to write it as e theta. If you guys recall from your physics for A, basically, if I have a vector r in here, I can change the vector r in the r hat direction, or I can change the vector r in the e theta direction, where e theta is simply in this direction. So here it's going to be dr, the change in the length of the vector. Here it's going to be the change in the direction of the vector. So this is r d theta. So the actual change is actually along both of them. It's the sum of the two. dr times r hat plus r d theta times e theta. So this length of dr, actually in general, since I'm writing dl, so let's stick with dl now. It's the same thing. It's equal to either change in the actual length by an amount dl in the radial direction, or change in the no, I'm sorry, by because the distance is r actually, so I have to write in here dr because we're measuring it from a distance somewhere from the wire. So this is r and this is r plus dr, okay, or r d theta in the angular direction theta. But I'm interested in BDL. I'm not interested in B or DL by itself. I'm interested in actually the dot product of the two vectors, B times DL. Obviously, R hat and E theta hat, they are perpendicular to one another. So it's going to involve zero dot product because the first one is length 1, the second one is length 1. But when I multiply both of them, there is a cosine of the angle between them, which is 90 degrees because they are perpendicular. Cosine of 90 degrees is 0. But I will be left with E theta dotted with E theta, and that's going to be length of 1 times length of 1 times cosine of 0, which is 1. So it's going to be involving just these two products, and that's going to be mu naught I over 2 pi r times r d theta, and that's it, because E theta times E theta is 1. So the r and the r cancel, and that is very important, because although I have an arbitrary shape, if I'm close by, the magnetic field is strong, but the change in r now is small. Whereas if I am very far away, the change in r is much bigger, and the magnetic field is weak, and these two effects cancel one another exactly through this relationship. Okay. D theta now changes from whatever the value is, and when you go through a whole cycle, we're going clockwise, by the way. The circulation is always defined clockwise. I mean counterclockwise. I'm sorry. So when you go counterclockwise, you're going to come back to your starting point. So you want a full cycle 2 pi. So theta changes from 0 to 2 pi. So at the end, if I calculate the circulation now around any closed path, it doesn't have to be circle, of BDL, I'm going to be left with mu naught I over 2 pi because the r canceled. And the integration now is just through theta from 0 to 2 pi of d theta. And that is equal to 2 pi, which cancels that 2 pi. And the answer is still mu naught I. So regardless of what path you're taking, you're always going to get to mu naught times I. That's a very important result. Now, what if the wire is not actually enclosed by this one in here? So what if I take another wire, another path, I'm sorry. So I have in here this one, but I take this path. Then in this case, I start, it doesn't matter where, if I start from here, the value of theta is this angle with respect to the x-axis. So this is theta naught. And you go around the path, and you're going to come back to negative theta naught, because you're coming in the opposite direction, and you're going to go back in here, but you're going to come back to the same value of theta naught. So the integration will be identical, mu naught I over 2 pi times the integral, but from theta naught to theta naught of this theta, and that is equal to 0. So if the path does not enclose the wire, you are going to get 0 contribution to the circulation. So only what matters in here is the enclosed currents. So if the current is not enclosed, you're not going to get any contribution whatsoever. The last point in here, and we would have had the entire theorem, is if I have many wires and one of them actually is going in, and this one actually is going in, and this one is going in. So I have a bunch of them. Some of them are coming out, and some of them are going in. So in this case, I have to find the contribution for any closed path in here. So who do you think we should invoke? What principle should be used? Do you guys remember? If I have more than one wire. So this has an I, this has an I, this is I1, this is I2, this is I3, this is I4, this is I5, this is I6, and this is I7. I have 7 of them. So do you guys, which principle that we should use in here? The principle of?
I'm trying to remember, but there's one on my mind. Man, it's on the tip of my tongue. Oh, yeah, there it is. Yeah, it was the very beginning. It was the very beginning that we learned that superposition. Yeah.
Yeah. The superposition principle will come in handy in this case. Here is the deal. This one, ignore all of the other wires. Just focus on this wire. It's going to have a circulation that is a mu naught I1. This one will have a circulation that is a mu naught I2. But of course, this is creates its own magnetic field B1. The circulation of B1 due to I1 is going to be mu naught I1. And the circulation of B2 due to I2 is going to be mu naught I2. And the circulation of, oh, now I have a problem. I have to deal with a sign. Here is the deal. Because I'm going clockwise, counterclockwise in this whole calculation, okay, for the circulation. If the current is coming out of the screen, that means the circulation is actually counterclockwise. The magnetic field is counterclockwise. Then take it positive. So this is going to be a positive contribution. This is going to be a positive contribution. This will be a negative contribution. That's all. Because actually, the magnetic field is opposite to the circulation. If you were trying to find B3 due to I3 is going to be, the magnetic field is actually along this path, is going this way. This is where B is, and you're circulating in this direction. This is the DL. So B and DL are opposite in sign. So this has to be a negative value because it's coming from the cross product. This one will give you a cosine of 0. This one is going to give you a cosine of 180 degrees. And cosine of 180 degrees would be a negative value. So this will be negative. This will be positive. This will be positive. This will be negative. This will be negative. As long as you stick to the sign thing, then you can say, due to the superposition, that the magnetic field due to all of this wire is just the sum of all of the magnetic fields. And that is property of actually the integral. And at the end, you're going to end up with the circulation of the entire magnetic field due to all of these currents on any closed path is going to be simply equal to mu naught times the sum of the currents enclosed. Okay, because any current that is outside falls under this classification, which is going to give you 0 contribution. Any current that is enclosed give you this one, and this is an algebraic sum. Does anybody remember the exam? This is similar to the exam, except there you had charges, and this one now you have currents, that's all, okay? So this, you need to be mindful of this stuff in here. So Ampere's law says, we're going to probably finish with it, okay? We still have another topic in this chapter, and then we can do problems. So Ampere's law says that the circulation of the magnetic field over any closed path is the product Don't forget that mu naught, please, in the calculation again, okay? It's very important. Product of the permeability in vacuum, permeability in vacuum, permeability in vacuum, it's a mu naught, but in other places it could be a different value. And this algebraic sum of the currents enclosed by the path. It's a very important theorem, and it's going to play the same role as the Gauss's law played it in the previous one. There is I know when we did, so I still have about, oh man, oh, we started late anyway. So, well, we still have about 2 minutes because we started late. So basically when we did Gauss's law, if you guys remember, this is how Gauss's law was saying the flux over any closed surface. So this is a closed surface, and it's in any actually surface. It did not have to be a sphere, by the way, was equal to Q enclosed divided by epsilon naught, or 1 over epsilon naught, the triple integral of rho dV, okay? When we use the divergence theorem, we ended up with the divergence of E is equal to rho over epsilon naught. There is a similar theorem in mathematics involving the circulation. The circulation now that we ended up with is actually equal to over closed path now, any closed path. So this is a line integral. The other one is a surface integral. This is just an integral over, and it's BDL now, instead of an area in here. You have a path now. And this one is actually equal to mu naught times the sum over the surface now. So this is an open surface now that is enclosed by that path. So if this is the path, this is the area that we're talking about, okay? So this is the surface in here. Actually, the current density times the surface area dA now, times dA, okay? Because this is an current density now. So if you use something called Stoke's theorem, okay, you are going to find actually the curl of B. The curl of B equals to simply mu naught J. Similar to this expression, okay? So divergence of E. So B curls, E diverges, okay? That's basically what these two expressions are telling you. So I'm going to stop in here right now. We still have to deal with the wires. Obviously, you're asking a question and you're legitimately asking it, and I hope that you are. Okay, tell me just the bottom line. How we're going to do our problems, and hopefully we can do that on Thursday, where we're going to discuss problems and see the relevant points of it. Obviously, we're going to come back to this Ampere's law, okay? We're going to be using it, so that's going to be useful for us. Do not forget the what we derived for the loop, which was this result. As I said before, this was actually an exam last semester, this whole thing. And don't forget also the wire, because this whole thing was derived, Ampere's law was derived from the wire, and we took it in general to be true, okay? So let's, we still have to deal with the two interacting wires, two wires carrying currents in this chapter, and we're done with it. And hopefully I see you guys on Thursday to discuss problems. Good?
All good.
Okay, so let me stop sharing the screen and let me stop the recording, and I will see you guys Thursday.
Alrighty. See you on Thursday, Professor.
See ya.